Yeah, so I'm going to be talking about specifically spend probably the last 30 minutes talking about this paper that we worked on entitled Large Language Models and Applied Econometric Framework. But what I want to do instead is I'm going to do this in a sort of slightly different style than a usual economics talk. And rather than spending sort of the full hour focusing on one paper, I want to provide a bit more of a directed overview for large language models for economists and people used to thinking about sort of empirical problems in economics. And in particular, I'm going to do so highlighting a series of papers that me and a team of co-authors in economics and computer science have worked on over the last year. And in particular, this is joint work with Jens Ludwig, Senda Malainathan, Kian Vafa, Justin Chen, John Kleinberg, and Peter Cheng, who are all postdocs, professors, or graduate students in computer science. So as a motivation for this broad space, I think that we're all very excited with, and that is, if you really look over the last 5 years and, really every single day, large language models such as, the GPT family and the Claude family really accomplish tasks that really no one thought was possible in the space of artificial intelligence and machine learning just 2 or 3 years ago. As a result of this, it really feels like this is a time where creativity is being unleashed in applied research. And there are many examples of large language models being used already. So to just give you a few examples of what are some questions we might think to tackle using large language models, suppose we're interested in understanding whether the market is using tacit information in earnings calls. Well, before we might have to get a bunch of undergrad RAs to read the text of all of these earnings calls. But now we could instead just directly prompt an open source large language model to predict stock returns from the transcripts of these earnings calls. Outside of asset pricing or finance, we would be interested in studying the effects of some policy change on political partisanship, for example, such as local closures around COVID. Again, now we could collect a data set of social media posts, prompt a large language model to label these media posts for partisan valence or identity, and then plug those structured regressors into some downstream causal inference framework that we would usually apply. And then perhaps a bit more out there, perhaps we could use large language models to find new insights about people. There's been a stretch of work that are using large language models as what people would call in silico subjects, where we prompt it to simulate people in various experimental conditions in order to explore the effects of different interventions as well. Now, across all of these, really exciting uses of large language models, I want to ask and think about like a very simple question. And that is, what precise econometric guidance should be given to researchers that want to use large language models in their empirical workflow? And thinking about that, there are many questions that immediately come to mind. For example, will their inferences be valid if they just take a large language model's output and pop it into their usual empirical strategy? Will their standard errors be correct? Or do they need to somehow adjust their estimation or inference strategy to account for the use of large language models? Now, I think the core challenge in trying to answer this question, there's a core technical challenge for how econometricians and statisticians engage with the field of artificial intelligence. And that challenge is that large language models are not a sort of single object. They are constantly evolving, new algorithms are developed, new training procedures are developed, seemingly every month. And these models are multifaceted and extraordinarily complex. As a result, when we're trying to provide guidance for applied researchers, we need to do so in a way that's not making intractable or high-level assumptions about really complicated computer science problems. In other words, it's important for us to be engaging with the field of modern AI with a degree of humility in the sorts of assumptions we write down about the outputs of these algorithms. So what I hope to do over the course of this next hour is I want to lay out what at this point I think is a pretty well-formulated applied econometric framework that can guide the usage of large language model outputs to answer questions that we're interested in. And in particular, this applied econometric framework has been built up across a variety of papers spanning econometrics, statistics, and data science more broadly. And really, this framework is going to provide guidance that depends on the specific use case researchers have in mind. So in particular, I'm going to distinguish between two types of empirical exercises. The first are going to be what we'll call prediction problems, where we want to take some collected piece of text and use that text to predict some downstream economic variable of interest. And the second is going to be what we'll call estimation problems, where we would like to use text in order to measure some economic concept that we're interested in studying, and then plug those measures into downstream regression or causal inference problems that we would like to solve. And briefly at the end, I want to conclude by arguing that really thinking rigorously about these familiar use cases is going to allow us to provide some guidance for the more novel uses of large language models that we're already seeing in applied research, such as using large language models as tools for hypothesis generation or human subject simulation, as I mentioned before. So to begin, let me just try to put a little more notation and make this idea of a prediction problem a little more specific. So as a running example that I'm going to return to throughout the talk today, let's imagine a researcher collects some text pieces that I'm going to denote by R, and they would like to use those text pieces in order to predict some linked economic outcome that I'm going to denote by Y sub R. So as a concrete example, you can imagine these text pieces are, for example, financial news headlines, and the economic outcome is going to be the realized return of the company about which the headline refers, say over the next 1 week window after the headline was published. So as an example, this headline could be the Bank of New York Mellon Q1 earnings per share misses its sort of estimates on Wall Street. So in this workflow, what would a researcher want to do? Well, they would want to use some large language model that I'm going to denote by some M hat throughout the talk in order to form predictions Y hat. And you can imagine them doing that either by directly prompting a large language model or by taking its pre-trained embeddings and fine-tuning it with some supervised learning algorithm. Regardless of how they generate these predictions, what the researcher would want to do is they would want to be able to calculate the large language model's sample average loss on their collected corpus, and then use that calculation in order to draw conclusions about how well the economic outcome can be predicted by text pieces R. So that's the problem we would like to solve when we're thinking about prediction. When we're thinking about estimation problems, I'm going to again introduce a bit of notation in order to tee up what's the core question. So again, let's imagine now a researcher collects some text pieces R, and to each of those text pieces, we can link some observed covariates WR. Importantly, we're interested in collecting this text because we often believe that text expresses some economic concept that would be costly to collect. But if we, the researcher, the expert researcher, read every document in the corpus, we could label each of these text pieces for this economic concept VR. So as an example, you could imagine a political economist collecting bills from the United States Congress. The text of those bills would be R. And to each one of those bills, the political economist would label each bill for the policy topic it refers to. So for example, this might be a bill to revise the boundary of Crater Lake National Park in the state of Oregon, in which case this would be a bill about the management of park services in the United States. Now, of course, the challenge is that these text corpuses often have hundreds, thousands, or if not millions of documents. And so we, the researcher, cannot read every single document in the corpus. But if we could do that, and we were to collect or measure this concept of VR across all documents, all we would want to do is plug that measure VR into some downstream regression. For example, we want to regress the policy topic on the partisan affiliation of the bill sponsor, and for example, report the coefficient beta star in that regression. Large language models enter the picture because they might help us solve a text processing problem. Rather than relying on us having to read every single document, let's just give it to a large language model. The large language model produces its own label V hat, and then we plug that into the regression. And so the core question for the use of large language models in estimation problems, will be of the form, does beta tilde LLM, the coefficient that is produced by this workflow involving large language model labels, recover the underlying regression coefficient that we'd be interested in? So let me just pause at this point to just see if there are any questions about really the two general problems that we're thinking about, prediction and estimation problems. And I think people should feel free to just unmute and ask questions, but if not, I will keep going.
Maybe just a very simple question about sample size. I mean, is the concept of sample size, does it even make any sense in this framework?
Great question. So I want to come back to that a bit later in the talk. But I think really the two things that are worth sort of keeping in the back of your mind is when we write down sort of statistical frameworks, we first have to have some notion of a population that we're studying. And from that population, we're going to be drawing samples, perhaps random samples from that population. And now when we're thinking about these sort of applications with text, where the text is every financial news headline in the United States for the last 30 years, every bill that was before Congress over the last 80 years, what is the right sense in which we should be thinking about what is the population we're interested in studying and how does the sample we have relate to it? That's going to be an idea that will arise sort of both when I talk about estimation problems and prediction problems later on. But let's come back to that.
There is another question in the chat from Tsing Tsing. Tsing Tsing, would you like to speak up? And another also from another person.
Yeah, I just want to understand because right now it's a text pieces are, and then it could be changing over time, and then maybe revisions over time. So this is more like a text sample instead of the numerical sample. So how actually incorporate those changes into the total sample you are doing estimation?
Good. So I want to think about sort of what is the simplest version of the problem where the researcher has access to a corpus of documents. Each of those documents is perhaps linked to some numeric outputs that they're interested in studying. So in this political economy example, think of each document as a congressional bill. Every bill is associated with some sponsor in Congress, and that sponsor has a partisan affiliation, a DW1 score, a bunch of things that political scientists and political economists study. And what the researcher would like to do is they would like to extract some concepts from the text and run regressions of that concept against these structured variables of interest or vice versa. And thinking about this sort of baseline setting is going to clarify what are the problems that will arise when we plug in large language model outputs, and then we can come back and think about more complex settings later on.
Also, Du Feng has a question. Would you like to speak up?
Sure. Yeah, my question is it really the output from the large language models? It depends on the instructions, right? How do we define the parameters or tell the large language model to do? So
Absolutely.
in this way, and perhaps the output from LLM will be biased because it really depends on how the instructors define the parameters and how do we sure you see the LLM output are fair and unbiased.
You're going to preview exactly everything I'm going to talk about over the next 30 minutes. But at this point, I'm being sort of intentionally abstract when I write objects like M hat being applied to a text document. Even if I think about, say, using ChatGPT or GPT-5 in order to generate a label interacting, say, with the API, I also need to include prompts. There's an entire literature in computer science on what people call prompt engineering strategies. Different prompt engineering strategies will result in different labels. And I'll show you that in empirical applications in economics, if you use different prompt engineering strategies in this workflow, you're going to get a wide variety of estimates, different signs, different significant levels. And so the problem is going to be, what do we do in light of that variability? But let me this is a perfect segue to sort of the next section of the talk, which is really...
We have another question by Russell, and then we'll let you go for maybe 15 more minutes uninterrupted. Russell, do you want to ask your question?
Can I ask one quick? What happened about the framework? So what happened if the VR is on the right-hand side rather than on the left-hand side? Like we measure sentiment and regress the sentiment on stock return rather than regressing on the sentiment.
Great. So VR being on the left-hand side or the right-hand side is not going to change any of this problem conceptually. It's going to change Really what I'm going to argue over the next 30 minutes is we have to think about, in the framework of estimation problems, we have to think about this like a measurement error problem. And once we are entered into the world of measurement error, the structure of bias and how we correct for bias is going to look different on the left-hand side versus the right-hand side. But again, I'm just going to focus on the left-hand side case through a lot of the discussion today, mostly because that's all you really need to focus on to get the core ideas. And I'll talk about how things change if it's on the right-hand side later on. But that's a great question. So just to keep moving forward a bit, I think you guys are all starting to set up exactly the segue I want, which is that in order to make sense of the usage of large language models in these prediction problems and these estimation problems, really at the core, we have to ask ourselves, how good are LLM outputs for the questions economists want to study? So then it would seem the problem becomes, well, how exactly should we as economists approach this question of evaluating the quality of LLM outputs? Well, a natural starting point would be to try to understand how exactly does the field of computer science approach this question? How do computer scientists evaluate the quality of large language model outputs? So now I want to do just a bit of background in order to get everyone onto the same page of how we think about LLM evaluation over the last 5 years. So in particular, in computer science and AI, much of the quantitative basis for the performance of large language models arises from what people refer to as benchmark evaluations that measure how well large language models perform on a specific collection of queries or questions. So, for example, these benchmark evaluations include well-known and popular evaluations of large language models on standardized exams that I'm sure you saw all around the release of GPT 3.5 and 4 about a year and a half ago. But evaluations are not just limited to these stylized evaluations on, say, the SAT and GRE. Perhaps the most important benchmark evaluations in computer science include collections of questions or queries that are aimed to evaluate what people call large language models, quote unquote, general intelligence. So just as an example, one popular benchmark in computer science is called HelloSwag. Folks in ML are very good at naming stuff, and it includes questions to test how well models perform on common sense reasoning tasks such as this. So in other words, HelloSwag is just a collection of questions, and one question in the HelloSwag benchmark asks, a woman is outside with a bucket and a dog. The dog is running around to try to avoid a bath. And then prompt the large language model to ask what would happen next. Of course, HelloSwag is not the only one. Another well-known benchmark in computer science is what's known as Big Bench Hard, which examines model performance on what are referred to as harder multi-step reasoning problems. So for example, one question in Big Bench Hard is the following. If you follow these instructions, do you return to the same starting point? Turn left, turn right, take 5 steps, take 4 steps, turn around, take 9 steps, and then you prompt the large language model to answer yes or no. So in other words, to answer our questions about prediction and estimation problems, you guys are already getting ahead of me and intuiting that we're going to have to evaluate the quality of large language model outputs. Well, today, much of the quantitative basis for general model performance in computer science comes from exactly these sorts of benchmark evaluations. And now in 2025, there are many more of these. You may have heard of these math competition benchmarks. There are specific coding benchmarks. There are also benchmarks for PhD level science questions as well. So this then becomes, well, if this is how computer science evaluates large language models, what can we as economists infer from these benchmark evaluations? Well, at their core, these benchmarks are literally nothing more than a collection of specific queries, like those questions in HelloSwag and Big Bench Hard that I showed you. So from benchmark evaluations, we of course learn the performance of a large language model on those specific queries in the benchmark. But of course, that means what we infer beyond that really depends on your view of what is the problem large language models are solving and how do these benchmarks relate to them. So what I now want to do is I want to present sort of what is one view of large language models that would allow you to connect benchmark evaluations to problems we work on. But I'll argue that that's really probably not the view you have in mind. So one view of a large language model is, let's just extract away from all of the work in AI and just treat it like some arbitrary mapping from queries the researcher is going to write down to outputs or responses that it's going to generate. In this view, we could just think about large language models through the lens of our classic supervised learning framework, where benchmarks are nothing more than a held out set of queries that are drawn from some distribution P over the types of queries we wish to deploy a large language model on. And so then when we report benchmark evaluations, we are learning the average performance of a large language model from this distribution of queries over which we might think to deploy a large language model. So in other words, we would just be applying sort of the lens of deep learning plus ImageNet to benchmark evaluations now of large language models and these reasoning questions. I think the problem with this view is it's not clear how you would even articulate what exactly is this distribution of tasks that would generate these benchmark evaluations. Put in another way, no economist I know is interested in taking a large language model and using it to answer randomly sampled questions from, say, the SAT, the LSAT, or the GRE, or even a random sample of questions from these reasoning benchmarks. So that doesn't seem like a promising route. Perhaps we might be able to learn more from benchmarks by thinking about large language models in another way. And in particular, I think a lot of the excitement surrounding AI today is as large language models perform better on these benchmarks, we believe they're going to perform better because after all, this is how we evaluate knowledge in people. So what I next want to do is I want to introduce this second view of large language models, and again, connect this back to standard benchmark evaluations in computer science. So the second view is that a large language model is somehow a brain in a box. In other words, LLMs understand and misunderstand the world like we do, or perhaps misunderstand or understand the world like the smartest person possible. And so in this view, benchmarks are a curated set of queries designed to evaluate this claim. But what I'll do over the next 15 minutes or so is I want to highlight sort of two streams of work that me and my group have been working on in computer science to try to directly evaluate this second claim. And then I want to come back after doing this to the question we started with: what can economists infer from benchmark evaluations? So first, let's think carefully about this claim that large language models think like people. In this view, if large language models are like people, they may not always be correct. Large language models hallucinate facts. People often misremember facts. But if large language models think like people, then perhaps large language model errors should be predictable to us. In this view, you might say that we have the ability to generalize about large language models using this view of sort of anthropomorphic bias, or what we call anthropomorphic generalization. So in this work that came out in 2024 in ICML with me and my co-authors, we set out to try to actually evaluate this claim. Can people actually predict the errors of large language models? So to do that, we elicited large data sets of what we call human generalizations, where we went online, presented subjects, an observed answer on some question A, and then we elicited the subject's beliefs about, given that you've seen some agent answer question A either correctly or incorrectly, do you believe the subject will answer question B correctly or incorrectly? So to give you an example, we pulled these framed questions from exactly the sorts of benchmarks that people use in computer science. So one thing our subjects were shown was we showed a subject a LSAT logic question, told them that an agent, either a person or a language model, got that question wrong, and then asked, how does that shift your beliefs about correctness on an adjacent logic question? We did the same thing across PhD level questions in biology and physics and other sources as well. So now, once we've gotten a data set about how people generalize performance from benchmark evaluations, we could then contrast LLM performance against people's predictions about performance on novel tasks. And what we found is that their large language models' performance appears to be systematically misaligned with human generalizations about correctness given observed benchmark performance. So as an example, this was done in spring 2024. So we showed people, for example, questions that a large language model got right about the marginal propensity to consume. At this point in time, it was the case that frontier large language models would get this question right, but would get simple arithmetic questions wrong. We showed people examples where large language models got particular logic puzzles right, but would systematically get variations of those logic puzzles incorrect, and so on and so forth. And what was very striking across this analysis was if you looked across large language models, people have an intuition that larger scale, more parameters, more data leads to better performance. What was striking to us is if you went and evaluated across large language models of different scales, larger large language models do not appear to be better generalized with human performance. And so this was interesting to us and to sort of the ML community because this was sort of initial early evidence of what anthropomorphic bias might look like in the use of large language models and how it might lead to bad deployment based on benchmark evaluations. So this is not just one paper. Over the last 2 years, there's been a series of work that shows that human intuition performs very poorly when predicting how large language models generalize to new tasks and new queries from observed performance alone. So one phrase you might have heard over the last 2 years is what people refer to as the jagged frontier of model performance. What this line of work now interprets the jagged frontier to be is that the jagged frontier is both a statement about frontier model capabilities and our inability to forecast performance on new tasks. So in other words, it's very difficult to go from benchmark evaluations to statements about performance on novel tasks. Furthermore, there is a related line of work in computer science that shows a related type of brittleness of large language models, where people show systematically that given a benchmark, you might find that a large language model performs well on some task A, but there often exists, and you can adversarially generate tasks A prime that are adjacent to A in some appropriately defined space that large language models will tend to systematically fail at. So in other words, what these two streams of work in computer science that has been built up in the literature over the last 2 years suggests it is difficult to reliably generalize about large language model performance from benchmark evaluations using just our intuitions. The argument that if a person could do A, then they could surely do B does not readily apply to large language models. And so we must be sort of careful if we're thinking about these sort of evaluations and just generalizing based on our vibes and intuition.
Sorry, could I ask a clarification?
Yeah.
What's the difference between these LLM brittleness and like just overfitting the model?
Good. So one view you could say, so I'd say the overfitting view would be if we want to treat large language models as sort of statistical learners, you might worry that, well, if we are training on these sorts of benchmark evaluations, we're going to get the ability to get them right. But if we sort of go off the benchmark, performance will drop off. I'd say one big difference between these brittleness examples is you can generate them off benchmarks as well. So you can take sorts of logic puzzles that are not in, say, Big Bench Hard and produce pairs, AA prime of logic puzzles where the language model will get one right, but not the other one. I think more broadly, you could also, I think there's like an interesting open question in this space, which is this logic of LLM brittleness has the flavor, if you're familiar in deep learning from, say, circa 2015, 2016, of what people would call sort of adversarial examples, which also has an intuition related to overfitting. So I think, more broadly, there is a lot of open space that still needs to be filled in our technical understanding of how you relate large language models to statistical learning. But I think there are examples of this that don't quite exactly fit the overfitting intuition. But it's a fantastic question.
So Ashesh, I'm going to let you decide, but my thinking is that since you have so many slides, more than 100 slides, maybe we should let you go until the end and then open the floor. Sure. But if you prefer to take questions, that's okay. But it seems to me that to cover as much material as possible, maybe we just let you go and then at the end we open the floor.
Perfect. Yeah, that sounds fine to me. I may pause it a few points if there are questions, like when there are natural section breaks.
Yeah, we only have like half an hour left, so I see that you have so much interesting material. So anyway, sorry for interrupting.
No problem. So, that's sort of one view of large language models, that they understand and misunderstand the world like us. And so we can forecast their performance well. Evidence over the last 2 years suggests that's not the case. But at the same time, you may say, well, we're not just interested in large language models because they are like people. We're interested in large language models because they can do truly miraculous things. And I think my favorite example of that comes from, if you read the original Sparks of AGI paper that came out in the beginning of 2023, some researchers had early access to GPT-4. And what they tried was to prompt GPT-4 to give a proof that there are infinitely many primes with every line that rhymes. And GPT-4 was already able to produce not only a valid proof, but also a pretty good poem. And then you can probe, this was not anywhere on the internet. This seemed to be something that was generated wholly new by the model. So when you see examples like this, it's not just that we think large language models are people, but we might believe that these large language models have uncovered what some underlying structure, or what you might call a quote unquote world model. And over the last 2 years, we've worked in this space as well. There's been a lot of interesting work in computer science to try to formalize what this idea might mean and derive its implications for how we think about evaluation. So I'm going to go through this part of the talk a bit faster. There'll be some notation, but I won't dive into much of the details. So if there are questions afterwards, I'm happy to dive in. So in order to ask this question of, does a large language model recover some underlying world model or structure, we need to have a model of a large language model and a model of structure. This is a very econometric activity. And so in this work, people tend to view this in a more implementation agnostic way. The algorithm is just a generative sequence model where those sequences are tokens for characters in a language. And then we want to evaluate based on the algorithm's behavior. So then this paper, sort of one of our core contributions, was to connect this view of generative sequence models to classic work in computer science that views sequences as being generated from a particular computational object that people refer to as deterministic finite state automata. You could think of this as sort of a hidden Markov model where there are some unknown states to us. And as you transition across states, tokens or strings are being generated. And that produces the language or text that we observe. Now, once you write this down, you can then introduce definitions of what it might mean for a large language model, or really a generative sequence model, to recover the underlying DFA. When is identification possible? And we provide some results about that in the paper. But that identification results, just skipping ahead a bit more, actually implies how we should think about evaluation. Again, connecting to some old ideas in computer science. So what we then do in the paper is we propose new metrics that can be calculated, and then we take them to the data to actually see how well do trained transformers actually perform in practice. So I'm just going to jump ahead to that particular evaluation. So what did we do in this context here? Well, what we did is we took a data set of taxi rides in New York City, about 13 million different taxi rides in New York City, where you see the starting longitude and latitude and the ending longitude and latitude of each ride. And then you can take those starting and stopping points and generate sequences of turn-by-turn directions. So for example, this is one taxi ride that started at whatever is the longitude and latitude of this starting point. I think it's somewhere like 40th and 5th or something like that, and then ended at this longitude and latitude, and then generated a bunch of southwest turns until it arrived at its ending point. So this is just sequence data. So what we can do is we can now develop or train large transformer architectures, the backbone of modern large language models, from scratch to do next token prediction on these sequences. And in particular, we focused on training two different transformer architectures, one with about 90 million parameters and another with about 1.5 billion parameters. And when we did that, we found, this transformer does amazingly well on next token prediction of turn-by-turn navigation in New York City. What's even more amazing is that you could take this pre-trained transformer that's just doing next token prediction on these sequences of navigation, and it actually appears to solve the shortest paths problem. In other words, it appears to have the functionality of Google Maps. If you provide the transformer with a new sequence, a new combination of starting and ending points that were not in its training data, it will generate a sequence of turn-by-turn navigations that not only goes from point A to point B, but does so in the shortest path possible on Manhattan. That is a sort of an example of seemingly that next token prediction generates emergent behavior that was not baked in at training. But what's surprising is if you take these evaluation metrics motivated by this more identification perspective, these trained transformers actually do quite terribly on the perform metrics. That's part one. Part two is you can show that this transformer architecture does not have a counterfactual model of the world. If you take the map of New York and insert detours and then ask it to connect from point A to point B, it can no longer solve the shortest path problem. But let's actually try to then visualize what is the implicit world model of these trained transformers. And so what we did in the paper is we applied some graph reconstruction techniques to sequences that were generated by the transformer. And if you look at its implied map of New York City, it looks like a complete and utter mess. It has many different flyovers, direct connections between intersections that would be physically impossible on the real map. And this was despite being very generous to the transformer and how we did this reconstruction. So what's coming out of this work on world models is sort of a puzzle. That is, versus one paper, there are many other papers studying other sort of sandbox domains, like physics examples or particular board games, where it seems like we're producing modern AI architectures that do well at next token prediction. If they do well on next token prediction in the setting where they're trained, they have emergent capabilities, but they have no coherent world model in the sense that if you introduce counterfactuals that wouldn't surprise you or I, they start failing miserably. So how is this possible? Well, what it appears to be true is that these large language sort of transgenerative sequence models, transformer architectures, rather than learning underlying structure, appear to overfit, going back to the question earlier, in the sense that they actually develop shortcuts or heuristics that work well for the problem they're trained on, but as soon as you move them to some different domains, start to fail dramatically. And this is a modern instantiation of a very classic idea in machine learning and persistent problem in high-dimensional settings, which Leo Breiman called in the early 2000s the Rashomon effect, sort of been rediscovered in deep learning under the lens of underspecification. But I'll be happy to take some questions about that later on. So just in the last, just to make sure we get through everything, let me just jump ahead and say what I wanted to summarize, sort of this coming from this view out of computer science, is it is very difficult to go from benchmark evaluations in computer science and our own encounters with large language models to make general statements about their performance on new tasks. Large language models don't generalize to new tasks like people. Our intuition is very bad at predicting where they'll perform well. And it doesn't appear that these algorithms uncover sort of robust underlying structure that might allow them to generalize out of domain into new tasks. So in light of this challenge, how should we as economists proceed with using large language model outputs in applied research? So again, just to go back where we started, we said, well, to make sense of empirical questions like prediction problems and estimation problems, we need to evaluate the quality of large language model outputs. So we then went to the computer science literature and asked, how do computer science think about this question? Much of the work focuses on benchmarks, but there's been a stream of work over the last 2 years that basically say benchmarks don't tell you what you think. So the challenge then for us becomes, how do we then provide guarantees for robust implied research in economics? So now I'm going to come to this applied econometric framework that has been developed over the last year or so across econometrics, statistics, and data science that addresses exactly this problem. So to start, we have to now think about how do we actually model large language models in our empirical workflow. And so rather than trying to directly model the inner workings of a large language model, what this framework is going to do is it's going to model a large language model exactly as empirical researchers interact with them. And in particular, we interact with them as black boxes to produce responses given any prompt, even though we don't really know what are the exact details, training data, or procedures used to, say, produce GPT-5. So coming back to another question from earlier, now when I write things like m hat of a particular text document R, we're going to think of that as combining many facets that go into the production of a large language model. So m hat is the text generator that returns responses to any string. The same large language model prompted in different ways would lead to different responses. You should think of that as a different choice of this text generator. And then we're also going to push in the back, the actual training procedures used to produce this mapping, whether that's next token prediction on top of instruction with instruction tuning, RLHF on the back end, or adding, more modern things like chain of thought reasoning over the last 2 years. For us, that doesn't matter. All that it produces is some m hat that produces responses when we prompt them. And one thing to note is what's going to be important is I'm going to carry around that this m hat is indexed by whatever training data was used to produce the large language model. And that's going to have important implications for how we think about the usage of these tools in prediction problems. So with all of that in mind, let's go back to the original prediction question that we were thinking about. So we thought of a researcher who had access to some text pieces and wants to use that text to predict some linked economic outcome. So think about the financial news example earlier. The researcher takes a large language model and prompts it to form some predictions y hat, and then they calculate the sample average loss of the large language model on their data set. So how can they use this workflow to draw conclusions about the predictability of, say, returns over the next week based on financial news headlines? Well, as another question earlier on alluded to, in order to define that question, we have to make precise what exactly is the inferential goal in this prediction problem. And so therefore, we're going to have to introduce the object of a sampling distribution that I'm going to introduce SQ over different text pieces, but also over possible training data sets of the large language model. The reason it's going to have both of those components is this sampling distribution or research context is going to capture two things that we're interested in. The first is over what text pieces do we want to generalize to? What text pieces do we want to assess the predictability of this outcome over? And the second is going to be, since the training procedures and data of these large language models are hidden to us, this Q is going to capture what do we know about what strings were used to train the large language model in the first place. And in this framework, the researcher would like to make an out-of-sample statement. They would like to evaluate the out-of-sample predictability of this outcome given the text pieces by evaluating its sample average loss. So the punchline of writing out all of this formalism is quite simply using large language model outputs for prediction. This workflow will be valid for the predictability question we've written down. It's an if and only if statement, if and only if the large language model the researcher uses satisfies no training leakage. No training leakage can be formalized as what looks like an omitted variable bias type interpretation. It asks how well or how much does language model performance in this prediction exercise co-vary with the probability that the large language model was trained on the text in the researcher's corpus. So in other words, no training leakage can be succinctly summarized as a researcher can use a large language model to do predictions, provided it has not been trained on the researcher's data set. That's not surprising. This should be exceedingly familiar from basic supervised learning because training leakage in large language model world constitutes a violation of the holdout principle. In supervised learning, if we were talking about lasso, random forest, or even deep neural networks, in order to evaluate predictive performance, you can't have trained on your test set. This is the same problem that is rising here. The challenge is, how exactly do you enforce no training leakage on large language models? These are large AI architectures that have been pre-trained and fine-tuned on extensive data. For closed language models like the GPT family, like the Claude family, Those details are hidden to the user, often for legal reasons. So how exactly are you to enforce that no training leakage actually is satisfied? Well, you should be worried about this question just from naive uses of large language models, because training leakage bedevils the evaluation of large language models on the benchmark exercises that I described earlier. In particular, if you just Google training leakage, natural language processing, you will find many blog posts of NLP researchers having a lot of heartburn about this problem. How exactly do you interpret benchmark evaluations if large language models have been trained on the questions in the benchmark? You can also show, so we did a little exercise based on this headlines data set, and some other researchers, Supratim Sarkar and Kian Vafa, in a related financial news headset data set, show that this is also a problem in economics applications as well. It appears that these sorts of text data that economists use oftentimes can enter into the training corpus of large language models. So if we want to use LLMs for prediction based on text, the core condition that we need to enforce is no training leakage. How exactly are we to enforce this if large language models are complex tools trained on data that we don't exactly know? Well, at this point, sort of the field's view is that the strongest solution to this problem is to use what are called open source large language models that have either a published training corpus or time-stamped weights, for example, published on Hugging Face. Why is this valuable? It's valuable because if the large language model has a timestamp and you are using a corpus that was generated after the timestamp, you mechanically know the training leakage.
I'm from DIT. Okay. Okay. So I just need your.
Is there a question?
I think somebody has unmuted, but she should be fine.
And furthermore, this takeaway has a clear upshot for what economists can be doing in the AI space, and that in particular, economists can actually be in the business of producing their own domain-specific large language models that mechanically satisfy this no training leakage condition. So for example, in finance and asset pricing, Supratim Sarkar, who was on the job market last year and is now at Chicago's booth, has published a freely available open source large language model family called Stories LLM that has timestamp training dates every year up to the 1980s. And that can serve as a foundation model for people wanting to use text for prediction in finance applications. So this is one concrete takeaway for applied researchers. If you want to use language models for prediction, the safest bet is to use open source large language models, and we can be in the business of producing them ourselves. Next, let me go back to this problem of estimation, where we think about using a large language model to infer some economic concept and then plugging it into downstream regressions. As some of the questions alluded to earlier, the core challenge here is going to be a measurement error problem. If we think that the large language model's labels do not actually equal the concepts that we're really interested in studying, then just plugging them into downstream regressions can lead to a wide variety of biases. So one thing you could hope to argue is, well, maybe large language models are exactly as good as ground truth. But hopefully in the first 30 minutes of the talk, I hopefully argue to you that that's actually a very challenging thing to defend at present. It's certainly not something that I would know how to defend in the context of a seminar. First, benchmarks that are used in computer science don't actually cover the use cases we're interested in economics, and it's very difficult to generalize off of benchmarks to new tasks. And furthermore, on sort of modern benchmarks that people now evaluate, frontier large language models are not perfect. So you would somehow have to argue that even though they are not perfect on CS benchmarks, they are somehow perfect in your economics application. Now, what does this mean for practice? So this was an exercise that we did back in 2024, where sort of frontier language models were GPT-4o, and people have redone versions of this with modern language models like GPT-5 and the Claude family and found similar results. So what I'm just going to show you from this exercise is we just took a random sample of 10,000 congressional bills. And for each bill, we have its text description, a bunch of structured covariates, and someone painstakingly went through and labeled each of these bills for their policy area. And that's going to be what we'll call ground truth VR. Then what I'm going to do is I'm going to take, at this point, it was 3.5 turbo and 4.0 with various prompt engineering strategies from the CS literature to label the policy area associated with each bill, V hat. And then I'm just going to compare two regressions. The first regression will be the one that uses the ground truth and reports beta star. And the second will be the one that just plugs in large language model estimates and reports beta tilde LLM for different choices of models and different choices of prompt engineering strategies. And if you do that, you see that just naively plugging in large language model outputs leads to point estimates that are all over the place. For the same specification, different models and different prompts can generate wildly sort of significant and negative estimates and significant and positive estimates. And this is true across all sorts of specifications someone might be interested in running in this data set. And as I mentioned, over the last year, people have replicated this sort of exercise in a variety of different text applications in economics and computer science. So this is not just a feature of language models circa 2024 or this application. This is a general finding that people have replicated across the literature. So, in light of this problem, well, what can we do? I think at this point, actually, what's nice is there is a clear workflow that can correct this problem. And the idea actually goes back to some classic ideas in the measurement error literature from the 1990s. And so the idea is quite simple. If we collect a random validation sample or a random benchmark from our corpus, where we actually measure ground truth, we can then robustly debias this plugin estimate. On that benchmark or validation sample, we can calculate what's the language model's error and then regress that error on the structured covariates of interest. And then the bias of beta tilde LLM is just exactly equal to that regression coefficient. So we can get back the coefficient we want by subtracting that off. Now, what you can show is... Can
I interrupt for a second? I'm sorry, but so I guess one difference that we have here is potentially we could use multiple LLMs.
Yep. I'll come to that.
Okay, sorry.
Yeah. No, but you're going in exactly the right direction, but a problem is going to arise, and that's a space where there's open technical problems that need to be solved. So, we can do the same exercise of setting up a sampling distribution and show that as the size of the researcher's corpus grows large, this debiasing procedure is consistent for beta star, asymptotically normal. We can calculate standard errors by bootstrapping. But there's actually going to be a clear value of using large language models here, which is that if the LLM outputs are at all accurate, then beta debias can be more precisely estimated than if you only use the validation sample on its own. And as I briefly alluded to, this is actually a very old idea. It goes back to results from Alan Kruger and John Bound in the early 1990s. And it's been recently revived in the ML and statistics literature over the last 2 years. So let me just illustrate this debiasing procedure in practice in the context of this congressional bills example. So what I'm now going to do is I'm just going to compare reporting beta tilde LLM, reporting this beta debiasing where we use a 10% validation sample and language model labels on the remaining 90% of the data, and a validation estimate that only uses the 10% validation sample. And these results, are quite stable depending as you vary the size of the validation sample as well. And then there's been recent results to think about the choice of that as well. So the first is, well, debiasing actually works. If you look across regression specifications that I showed earlier, debiasing actually generates point estimates that are approximately unbiased for the beta star of interest. Furthermore, debiasing actually leads to correct coverage of confidence intervals for both 3.5 and turbo. A 95% confidence interval actually has 95% coverage across all specifications, whereas naively plugging in can lead to quite substantial size and coverage distortions. What's actually quite interesting is validation data, when used correctly with large language model outputs, can lead to an improvement in precision. So what I'm comparing here is the mean squared error of the regression estimates that ignore the large language model entirely, that's plotted in red, against those that incorporate the validation data and the large language model labels with appropriate debiasing. And again, across all specifications that we've encountered, debiasing actually led to tighter standard errors than if you ignored the large language model altogether. Now, coming to Jose's question, everything I said there hinges on the ability to collect benchmark data. What if you can't actually collect this validation data? Is there something you could do? Well, one view would be, let's actually just, drop the perspective that there is some true concept that we're willing to study, and the only thing we're studying is the labels produced by the large language model. In other words, the object of interest is in fact beta tilde LLM, not beta star. I think if you went down this path, you'd have to ask and answer sort of, I think, uncomfortable questions, which is that different large language models produce different labels. So if one researcher studying congressional bills used, say, GPT-5, and another researcher studying that same congressional bills data set used instead DeepSeek or Gemini, are they somehow asking different economic questions of interest? Or when a new model gets released, do we have to then go back and revisit all research that was conducted with sort of now inside the frontier models? So I think this is a route that we would not be willing to.
I'm just going to interrupt you for a second just to make an announcement. I think we're going to let you go until you finish, and we're recording this, so if people have to drop, they can come back and they can see the end of the seminar. But we're just going to let you go to the end.
Yeah, great. I just only have like a couple more minutes of material, and then happy to stick around for questions. So then I guess now coming back to Jose's question, if you're not willing to accept the view that there is no ground truth, you think there is a VR that you would like to measure, maybe we could use the fact that we have many large language models, or even within a language model, we could have many different prompt engineering strategies. So could we collect many large language model labels and combine them in some manner? One view would be that's actually correct, provided the large language model labels are independent of one another. If they were independent of one another, then again, classic results in the measurement error literature would actually tell you that things like the base rate of the concept and those regression coefficients are in fact identified. The problem is that large language model labels are, of course, not independent from one another. There is substantial overlap in the pre-training and fine-tuning data across families of models. And furthermore, within a model, it's been trained in the same way. So different prompt engineering strategies produce labels that are extremely correlated with each other. And this is something that has, again, been systematically documented in benchmarks from computer science. And I'll point you to this recent paper from earlier this year. So, an open challenge here would be, in the absence of benchmark data, what can we do? And right now, sort of the state of the art is, unfortunately, debiasing with validation data is the only sort of rigorous procedure to get back unbiased estimates. But this is a fantastic open space to be working in. So, with that, let me just wrap up and sort of summarize what I think the state of the art is for researchers wanting to use large language models in applied research. And that is, in light of the work coming out of computer science, we know LLM outputs are imperfect. They're often better than the alternative, which is nothing. So how do we incorporate them in applied research? Well, they're really just a simple workflow that you can ask yourself. First, are you working on a prediction or estimation problem? If it's a prediction problem, then the assumption you need to defend is no training leakage. And the safest way to enforce that assumption is to use open source large language models with published training data or published in time-stamped weights. The second is, if you're working on an estimation problem, the fork you face is, can you collect ground truth measurements on a validation sample? If you can, then you can evaluate the error of the large language model and debias the outputs for the appropriate downstream estimate you're interested in. And if you can collect measurements, then at this point, you have to acknowledge the sensitivity that your answer may vary based on the model you have chosen. And that's a place where, quite frankly, there's more technical work that needs to be done. So taking a step back, what I want to summarize is, over the last 25 years, I think the success of econometrics has been in developing an applied toolkit for causal inference. If you're doing a diff and diff, you have to defend the parallel trends assumption, and we have ways of thinking about sensitivity analyses. If you're doing an IV, you have to defend exclusion, independence, and monotonicity. And what we need now over the next 10 years is the same sort of applied toolkit to allow researchers to use outputs from modern AI tools in research. And over the last year or so, I think what econometrics and statistics has delivered is at least version 1 of such a toolkit, where the key question is, are you working on prediction or estimation problems? And in light of that, we can appropriately use, possibly imperfect, but still quite impressive AI outputs to tackle important empirical problems. And as I flagged, there's a lot of technical work that's still to be done. So I'd be happy to talk about sort of where the state of the art is along those dimensions. But thanks so much for the chance to talk to you all. There's a lot of material. I went kind of fast. So happy to stick around if there are any more questions.